Ladies and gentlemen, welcome to my talk on resource awareness in data processing. In my talk, I would like to convince you that we also need to look at what it takes to implement all these nice CPS and IoT systems in the future. So I believe it's not sufficient just to look at all the nice applications that are feasible, but we also need to consider whether or not we can actually implement all these nice applications. Towards this end, I would first of all like to convince you that in general there is a need for complex algorithms and a need for considering potentially huge amounts of data. I would like to convince you by pointing towards already existing demanding applications like driver assistance, weather prediction, and mudslide predictions. In these cases, we do have very demanding processing requirements, and we also have huge amounts of data. And I think that in the future, we are going to see more of such applications in the future. So therefore, I believe that in general, future CPS and IoT systems will have to execute complex algorithms, and potentially we have to process huge amounts of data. So as a result, I think there will be demanding requirements, both in terms of the performance of the processes, in terms of the communication bandwidth, and also in terms of the amount of data that needs to be considered, and all of this in potentially constrained environments. This has led, by the way, to the proposal of the DFG-supported Collaborative Research Center, SFB 876, which focuses on the analysis of big data in constrained resource environments. Which constraints do we actually have to consider? Well, this slide contains a large list of constraints and objectives. Since constraints and objectives can in one way or the other easily be interchanged, I would like, for the sake of simplicity, to just talk about constraints in the future, in the remaining part of this talk. So which constraints do we consider? Well, first of all, we need to guarantee the required performance, but then we also need to have energy efficiency. We need to consider thermal constraints, timeliness constraints, resilience constraints, and there may be quality metrics such as the quality of service. And then there are many more constraints. In fact, this list is very long, and the fact that this slide is rather congested corresponds to the situation where we do have to consider many constraints and objectives. And I'd like to point towards the fact that if a certain design just fails to meet one of these constraints, then this design might be already dead before it's introduced into the market. So please be aware of this increasing list of constraints. In the following, I would like to talk about the first 6 entries in this list. Other entries may be discussed by other speakers, but not by me. So first of all, let's look at performance constraints. There is, in general, the trend towards needing higher performances. This has led some time ago to the introduction of multi-core processes. This led to more seriously considering parallel processing, but I think more consequences of this change towards parallel processing still have to be considered. This consideration also needs to be aware of recent trends, like the trends towards GPUs and ARM's big-little architectures as particular cases of more heterogeneous architectures. We're not pretty sure about the memory architecture of the future. Are we going to see consistency in future memories or not? And also we need to carefully look at parallel programming even more. We need to look at models. We need to look at synthesis. The cores that are available right now, they need to be managed, so we need thermal management. We can take advantage of redundancy, and all of this has to be considered even more in depth than what has been done so far. A particular bad area is that of guaranteeing worst-case execution times. Unfortunately, most of the available multi-core processors use shared resources, and therefore available execution time guarantees are typically not very tight. Second constraint that I would like to consider is the energy efficiency constraint. There are various reasons why we could be interested in energy efficiency, starting with global warming in this list and ending with energy as a very scarce resource. Now, whether or not for a particular CPS or IoT type we have to consider these reasons depends very much on the particular power consumption. So in this table, I suggest that you look at those cases where boxes are not ticked. You see that for sensor networks, for example, we have a very small impact on the global warming. And also for plugged systems, we don't really have energy as a very scarce resource. In this context, I'd like to point towards one particular example which demonstrates the type of new designs that we might see in the IoT era. This is a design that was performed by a local Fraunhofer Institute for Logistics. In this design, we have a box which is aware of its content. There may be certain products there in the box, and the box is able to communicate its content to the environment. For this, certain wireless communication is needed, and also we need, in this case, two processes. All of this has to be powered from the energy which is available in the environment. So for that purpose, there is a solar cell, and the light which is available in the storage facility has to be sufficient to generate enough power in the solar cell so that processes and communication can actually be powered up. So I think this is a very nice example of the type of systems that we're going to see in the future. As a next constraint, I'd like to consider thermal constraints. We know that we're living in an area where thermal constraints are important, as is well known from mobile phones already. We know that, for example, in mobile phones, even charging sometimes has to be stopped because otherwise the device would get too hot. We are moving more and more towards a dark silicon era, which means that certain parts of our chips might not be powered up for thermal reasons. Overall, we cannot guarantee thermal stability at the hardware level anymore. We have to use software to guarantee thermal stability, and this even leads to a new type of viruses where the viruses could potentially overheat a certain circuit. I predict that in the future we are going to see many complex trade-offs. So, for example, we might drop some less important computations if otherwise our chips would get too hot. The next constraint that I'd like to consider is the timeliness constraint. We do have this constraint because cyber-physical systems comprise some physical part, and this typically leads to timing constraints. Unfortunately, many of the available circuits are designed only for good average case timing, such as this multi-core system which has a shared cache, which leads to very poor timing predictability. So in general, multi-cores and communication are very frequently very poorly timing predictable. There are more areas that potentially create problems, such as the memory system. We also know that in computer science we didn't care so much about precise timing models, and I predict that as a trend it might become even more difficult in the future, because we are seeing more and more mixed criticality systems, and we are going to see more virtualization, and this all leads to poor timing predictability. Also, I think there is a trend towards consideration of the overall timing of applications rather than considering just the worst-case execution time of a single thread. Again, in this area, I think we need more flexibility. So, for example, we might drop certain computations if we wouldn't meet the deadline anyhow. Such flexibility is also needed for taking into account the impact of future hardware technology, which is known to be less reliable because of the shrinking dimensions. Because of shrinking dimensions, we are going to see more and more faults. So in a way, this is like driving your car at higher and higher altitudes. The effect of shrinking dimensions is also already considered in the NSF Variability Expeditions program. I think that in the future we have to accept that there will be no perfect execution platform anymore. We must consider the impact of faulty hardware. Again, this leads to complex trade-offs, and again, this can lead to approximate computing. You might have to be happy with certain computations to be done not precisely. These effects are actually considered when we look at quality metrics such as the quality of service. We know that there are certain application areas such as audio and video where we don't really need exact results. Also, there are control loops where noise has to be considered anyway, and there are some designs in statistics where a 100% guarantee cannot be given by design. So if we take into account this flexibility, we might gain something in terms of some objective like energy or heat. Overall, I think this leads to a kind of approximate computing where we do rather complex trade-offs. As an example, I would like to point towards a trade-off that we have computed there for the pulmonobiovirus sensor. For this biovirus sensor, we found that there is a trade-off between the detection quality and the consumed energy. If you're going for the best detection quality, you need to burn quite some energy. But if you're happy with a reduced detection quality, then you need less energy. So I think this is a very nice example of the type of trade-off that we're going to see in the future. Now, in order to perform these trade-offs, designers must be aware of the various areas that are involved. So in this case, we must be aware of computer science, electrical engineering, and physics. In other cases, even other disciplines might be involved. So in order to take advantage of these trade-offs, from my point of view, we must be removing the walls between the various disciplines, which I know is already difficult in research. But nevertheless, it does generate some benefit, as can be seen on this slide, where we see schedules for the execution of certain prediction models. This upper half corresponds to schedules that have been generated taking knowledge from real-time systems into account, and the lower half indicates schedules that were generated by the initial approach proposed by the Department of Statistics. So you see, if we take knowledge from real-time systems into account, then we can better exploit the availability of multi-core systems. And in this case, this means that this leads to a better prediction of the impact of medication for certain cancer patients, because we can have more model evaluations in the same amount of time. Now, removing the walls in education, however, is even more difficult. As a contribution in this area, I try to figure out what are the essentials that need to be known by students working in the area. And therefore, I wrote a textbook where all the essential knowledge from my point of view is covered. And also there are related videos that are used by students all over the world. However, this is only a partial solution, because if we would like to go for an integrated cyber-physical educational program, then we very easily hit the very tight ceilings for the total number of credits, and therefore it's very difficult to design such an integrated program. To conclude, I'd like to mention again that in general I see the need for very complex algorithms and for huge amounts of data and corresponding data analysis techniques. I think that these algorithms need to be executed in a way where we are aware of the resources, of the constraints and the objectives. There is an increasing list of constraints and objectives. This list has been covered in this presentation, and I see that in the future we will need to have more complex trade-offs between these objectives, sometimes at design time, but potentially also at runtime. In order to perform these trade-offs, we must be trying to remove the walls between the various disciplines which are involved, which I acknowledge is already difficult in research, but even more so in education. Thank you very much for your attention. I hope that you liked this presentation. And if you have some question, please send me an email. You will find my email address very easily on the internet if you just look for my last name, Marwedel. Thank you very much.